The natural world is full of quiet events. A leaf unfurls, a seed takes root, and sometimes a piece of fruit falls from a tree. In the county of Lincolnshire, England, one such ordinary event is said to have sparked extraordinary thoughts. Imagine a still afternoon, perhaps in the late summer of 1666. The air is calm. A young man sits in an orchard, lost in thought. This was Isaac Newton. He was not yet the celebrated figure we know today. He was simply observing the world around him, as curious minds often do. The story, perhaps embellished over time, tells of an apple detaching from its branch. It fell, as all apples do, straight to the ground. Many would have seen this and thought nothing more. A simple, everyday occurrence. But for Newton, this small event was a puzzle, a question whispered by the earth itself. Why did the apple fall downwards? Why not sideways or even upwards? This seemingly simple question began to stir something profound within his mind, a curiosity that would eventually reshape our understanding of the entire cosmos. Isaac Newton's entry into the world was itself a fragile beginning. He was born prematurely on Christmas Day in 1642, in the small hamlet of Woolsthorpe by Colsterworth. This was a time of great upheaval in England, with the Civil War raging. His father, also named Isaac, had died 3 months before his son's birth. The infant Isaac was so small it was said he could have fit inside a quart mug. His survival was uncertain, a tiny life clinging on in a world of turmoil and personal loss. His mother, Hannah Ayscough, remarried when Isaac was just 3 years old. Her new husband, the Reverend Barnabas Smith, did not wish to take on his young stepson. So, Isaac was left in the care of his maternal grandmother, Marjorie Ayscough, at the Woolsthorpe Manor. This separation from his mother during these formative years must have been a profound experience. Childhood is a time for bonding and security, and young Isaac found himself in a world that felt somewhat detached. He later confessed to a deep resentment towards his stepfather and his mother for this abandonment. When Isaac was around 12 years old, he was sent to the King's School in Grantham to receive a formal education. Initially, he was not a standout student in the traditional academic sense. Reports suggest he was often inattentive in class, his mind perhaps elsewhere, absorbed in his own intricate thoughts and observations. He was not drawn to the classical curriculum of Latin and Greek as much as he was to the world of mechanics and construction. His true passions lay not in reciting ancient texts, but in understanding how things worked and in creating with his own hands. It was during his time in Grantham that his innate ingenuity truly began to shine. He lodged with the local apothecary, William Clark. This environment provided him with access to books and, crucially, the space and perhaps encouragement to experiment. He became fascinated with mechanical devices. He meticulously crafted intricate models, including a small windmill powered by a mouse he humorously named Miller. He also built water clocks and sundials, demonstrating a remarkable early grasp of practical physics and engineering principles. In 1661, at the age of 18, Isaac Newton embarked on the next stage of his intellectual journey. He entered Trinity College, Cambridge. He enrolled as a subcaesar, a student who performed domestic tasks for wealthier students and fellows in exchange for reduced fees. This status would have reinforced his solitary tendencies, setting him apart from some of his more privileged peers. At Cambridge, the curriculum was still heavily based on the works of Aristotle, but Newton soon discovered the more modern philosophical and mathematical ideas of thinkers like Descartes, Gassendi, and Copernicus, often through his own independent reading. His formal studies were, by his own later accounts, somewhat unremarkable in these initial university years. He was a quiet, diligent student, but there was little to suggest the revolutionary genius that was about to awaken. He explored various subjects, including optics and mathematics, often delving deeper than the prescribed texts. He began to question the established Aristotelian views of nature, finding them insufficient to explain the phenomena he observed and read about. His mind was a fertile ground, quietly absorbing information and preparing for a period of extraordinary intellectual growth. Then, in 1665, a dramatic interruption occurred. The Great Plague swept through England, forcing the University of Cambridge to close its doors. Section 5. The Universe in Motion, Newton's Laws Revealed. One of the most monumental achievements of Isaac Newton was his formulation of the 3 laws of motion. These laws provide a fundamental framework for understanding how objects move, or indeed remain still. They are the bedrock of classical mechanics. The first law, often called the law of inertia, states that an object at rest will stay at rest, and an object in motion will stay in motion with the same speed and in the same direction unless acted upon by an external force. Think of a smooth stone resting on the ground. It will not move unless pushed or pulled. Similarly, a ball rolling across a perfectly frictionless surface would, in theory, roll forever. The second law of motion introduces the concept of force in relation to mass and acceleration. It states that the force acting on an object is equal to its mass multiplied by its acceleration. This means that a greater force is needed to accelerate a heavier object, or to make an object accelerate more quickly. Imagine pushing a small cart versus pushing a large, heavy wagon. The wagon requires significantly more effort to get it moving and to change its speed. This law allows us to calculate precisely how forces affect the motion of objects, a cornerstone of engineering and physics. Section 6. The Invisible Tether, Understanding Universal Gravitation. Beyond the laws of motion, Newton's genius gifted us with the theory of universal gravitation. This was the profound insight that connected the falling apple to the celestial dance of the moon and planets. He proposed that every particle of matter in the universe attracts every other particle with a force. This force is directly proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. This means that the more massive the objects, the stronger the gravitational pull between them. And the farther apart they are, the weaker the pull becomes. This was a truly audacious idea. Before Newton, the heavens and the earth were often considered to be governed by entirely different sets of rules. Terrestrial objects fell, while celestial objects moved in perfect eternal circles. Newton dared to suggest that the same force responsible for pulling an apple to the ground was also responsible for keeping the moon in orbit around the earth, and the earth in orbit around the sun. Section 7. A New Language for Change, the Dawn of Calculus. While grappling with the complexities of motion and gravity, Isaac Newton recognized the limitations of existing mathematics. He needed a new tool, a new language to describe and analyze quantities that were constantly changing. This necessity led him, independently and around the same time as the German philosopher and mathematician Gottfried Wilhelm Leibniz, to develop calculus. This was not merely an extension of existing algebra or geometry. It was a revolutionary way of thinking about rates of change and the accumulation of quantities. Calculus is broadly divided into two main branches: differential calculus and integral calculus. Differential calculus is concerned with instantaneous rates of change, how quickly something is changing at a specific moment. Think of the speed of a falling apple not just as an average, but its precise speed at any given point in its descent. It allows us to find slopes of curves and velocities of moving objects. Newton initially referred to this as his method of fluxions, considering quantities as flowing or changing over time. Integral calculus, on the other hand, deals with the accumulation of quantities. Section 8. Beyond the Equations, the Man of Many Facets. While Isaac Newton is celebrated primarily for his scientific breakthroughs, the man himself was a complex and multifaceted individual, far removed from the serene image of a purely rational thinker. He possessed an intense, almost obsessive personality, capable of ferocious concentration for extended periods. When engrossed in a problem, he would often forget to eat or sleep, driven by an insatiable curiosity and a relentless pursuit of understanding. This intensity, however, also contributed to a famously prickly and secretive nature, particularly when it came to his work. Beyond physics and mathematics, Newton dedicated an enormous amount of time and intellectual energy to subjects that might seem surprising today. He was deeply immersed in the study of alchemy, the ancient pursuit of transmuting base metals into gold and discovering the elixir of life. His alchemical manuscripts, filled with cryptic symbols and recipes, outnumber his writings on physics. He believed that ancient wisdom held secrets to the workings of nature, and he pursued these studies with the same meticulous rigor he applied to his scientific investigations, hoping to uncover the fundamental principles of matter. Section 9. A Titan's Legacy: How Newton Reshaped Our World. Isaac Newton's work forms the bedrock of modern science. His laws of motion and universal gravitation provided a comprehensive understanding of the physical universe. Newtonian physics reigned supreme for over 2 centuries, explaining phenomena with astonishing precision. His insights fueled the Industrial Revolution and laid the groundwork for advancements in optics. Newton's laws remained profoundly relevant, providing an accurate framework for everyday physics.